start by an announcement. So I've just checked, as I told you, right? We have 5 more weeks to the end of the semester. It's already started already. And 1 week I will be away. So we actually have 4 weeks to the end of the semester. Yeah, of course I'm the last week of February. So we have basically 2 weeks now, then 1 week which I'll be away, and then 2 weeks which I will be back. Which means actually we're losing only 2 hours because one of the Tuesday is going to be a day election day, so there is no, but still. So given what you filled in the table on Tuesday, the easiest solution for everybody, as far as I could tell, is to head up 1 hour lecture on Thursday. So rather than having Thursday 4 to 6, we'll have 4 to 7. So 3 hours lecture. We'll make a break in the middle, right? 3 hours is too much. But is that okay with you? Mm-hmm. It's an announcement. So this will be basically each of the 4 weeks. So we can have 4 extra hours. Okay, so Thursday.
Sound good.
Thursday lectures 4 to 7.
Every week. It is what it is. I mean, we have a short semester. It's a pity because we're just starting to get into the fun part of the course. Yeah. Fun for me, I don't know if for you. That's okay. And I did not see that there was any problem with that. So, last time, we're still speaking about basically QED, right? Maxwell's equation, photon, Klein-Gordon. What we did last time, or even the time before that, right? We looked at the solution for the photon, basically. Right? So we said the photon,
we look as A mu is A epsilon mu of P E minus I P mu x.
And we ended up finding that there are 2 polarizations, basically. Epsilon mu, epsilon mu minus was 1 over square root of 2, share 1 minus I0, and epsilon mu plus is minus 1 over square root of 2, 0, 1, I0. And then I argued that these are really related to the photon spin. Basically, I did that by showing that these are eigenvalues of the eigenstate, sorry, of the angular momentum in the z direction, and propagation plus z direction. Then I define this thing which is called helicity, H, which is S dot P, basically over P. That is basically the component of the spin along the direction of momentum, normalized. I said this H gamma is plus minus 1. Then that was actually not the last lecture, but the lecture before that. The last lecture, which actually I consider as a tutorial more than a lecture, we discussed discrete symmetries. I said there are 3 discrete symmetries. We discussed 2 of them. One is the parity.
Which is essentially R goes to minus R.
This is in all directions, all 3 directions, spatial directions. So it's a flip of the coordinates. Then I said, there was something which was a bit, somebody asked me about that, so let's clarify things. I said the following: under parity, the electric field changes, reverses sign, right? So E of R goes to minus E of minus R. B does not change sign. B of R goes to B
of minus r. And then a of r goes to minus a of minus r. And phi of r goes to phi of minus r. Phi also does not change sign. That means that the photon, which is represented by A, has an intrinsic parity. P photon is equal minus 1. Then we spoke about the other symmetry, which is called charge conjugation. That's an operator which is called C. And again, this is another discrete transformation. It takes a charge and turns it into the opposite charge. Now, essentially, this means replacing a particle with the antiparticle. Namely, if you take a charge, for example, with the pi and plus, you'll get a pi and minus. Now, there are several particles, such as the photon, which are their own antiparticles. And so we can say that these are eigenstates of the charge conjugation. Right? And the question is, hold on, and the question is, what is the eigenvalues? Now we said that under charge reversal, right, we have that rho goes to minus rho and j goes to minus j, which means that A mu would go to minus A mu, which essentially means that under charge of a photon, you will get a minus of a photon. So you said that the charge of a photon is minus 1. Now, somebody asked me to elaborate on that point. I tried to figure out, I mean, this is the simplest explanation that one can find in any basic test. If you're not convinced, I mean, the question was, how can it be that the photon is its own antiparticle? So how can it be that under charge you get a minus sign? So first I showed you, right? Under charge conjugation, what you get is that the A goes to minus A. So that's the easiest way to think of it, is to now switch the field. Another way of thinking of it is the idea is the fact that the photon has a spin, right? So what will happen under charge, right? It will basically flips the direction. And that is the thing. So one way to look at it is saying, okay, let's say, so let's say I have a photon, which has a momentum and a helicity. And I'm operating on that as a charge conjugation. What I'm going to get is the antiphoton. I'm putting this quotation because it's really a photon, right? With a charge and helicity, with a momentum and helicity, and with some k. I'm going to argue that this k is minus 1. The question is why it is a minus 1. Right? So how can we get to an antiphoton with the same momentum and helicity from if we start from a photon? Well, we have another way of taking the complex conjugate of a photon. So if we take a complex conjugate operator of a photon, so P and H, we will get the antiphoton with a P and a minus H. No way. Again, because of the helicity, H essentially got a minus sign because the spin now is reversed.
Well, why is H a vector?
H, sorry, it's not a vector, it's a scalar. Thank you. Of course, it's a scalar.
The second row.
But you did get an extra minus sign. Right, because now it's an anti-photon with some minus h. So how do we get to the plus h? If the photon is moving in the z direction, we have to flip in the x or y direction by 180 degrees. Right? So we take the rotation, let's say in the y direction, by 180 degrees of that. What do we get? Get an extra minus sign up front. So we get a minus gamma P and H.
Wait, why is flipping it in the y direction doesn't flip the spin? The momentum, sorry.
It does flip the momentum. So we get the minus here.
Ah. And
That's
that's
all.
only the momentum.
Yes. So that's now again. You can think of it in these terms. There it goes, or you can think of it in terms of the photon has this intrinsic spin. At the end of the day, these are equivalent. So whichever you feel more comfortable. This is, I guess, is easier because this is if you look at the standard textbooks, this is normally what you find there. This goes slightly beyond what you find in most textbooks. Yes.
Is it right to think about that? That if you are flipping the charges and the photons are the electromagnetic interaction, it flips the electromagnetic.
In a sense, yeah. Okay. Now remember, if the charge, right, takes one particle, takes it into a different particle. Only if the particle, so generally a particle is not does not represent a eigenstate of the charge operator. Only those particles that happen to be their own antiparticles do represent it. Okay? Good. Clearing that. All right. Yes.
Or also, if a particle is chargeless, it's also not always his own antiparticle, right?
Well, the photon is basically chargeless.
לא, אם כאילו יש חלקיקים לא טעונים שהם לא, ניוטרון למשל, לא אנטי חלקיק שלהם.
נכון. Okay. So I put a small summary. I will erase that now. Let's put a summary of the key properties of the photons that we find. So, summary of the photon. So one, it's a massless particle. P mu is equal to 0. 2, it is a vector. So although it only has 2 degrees of freedom, we really describe it by a 4 vector. It's a vectorial particle. It has 2 degrees of freedom. Which we call polarizations, right? So transverse, namely epsilon dot p is equal to 0. Has spin 1. And helicity, H gamma is plus minus 1. And has a parity, P gamma minus 1 and C gamma is a minus 1. That's why we said that it's written as a J and C is 1 minus minus. That's a standard notation that you find in PDG tables. All right, questions?
What is the charge conjugate of a neutron, for example?
Just to flip the
I'm not sure of that. I don't remember by heart. So I don't want to say something which I'm 100% sure about. Go and check.
Okay.
All right. So what I'm going to do today,
yeah. Don't you just flip the quarks neutron?
it will, but I don't. Yes, it will, but I can easily check that. Okay. Now, what I want to do today is to talk about the Klein-Gordon equation and also the Proctor equation. So Klein-Gordon equation. Which is actually quite an important lesson. Okay, so a photon is massless. Now what happens if you want to speak of massive particle? Massive and scalar. When I say scalar, right, that means it is a it is a function of the location in space, which is a vector, of course, but it gets scalar values. Okay? If it gets scalar values, means it does not change under Lorentz transformation. Does not change under Lorentz transformation. This, by the way, means that it cannot be described by Schrödinger's equation. Why? Why not?
The Schrödinger equation is not invariant.
Changes.
So this part, it has a first derivative in time and second derivative in space. Right? But you know, the relativistic version of Schrödinger equation is going to be quite straightforward. Right? Where's the problem?
That's the part.
We derived Schrödinger's equation, right? What was the origin of the problem? That we used what?
Non-relativistic energy
Right.
conservation.
The problem was that so in Schrödinger's equation we used E is equal to P squared over 2m, which is non-relativistic, right? Non-relativistic. Fixing that is quite straightforward, right? For massless particle, you had D'Alembertian phi is equal to 0. So for massive particle,
Yeah.
simply
I'm
use
sorry, for massless it's the inversion of the A mu, right?
if it's a vector. Now I want to speak of a scalar, so it's just fine.
Okay.
Even simpler. If it's a vector, it will be an A mu.
Mm-hmm.
It's just a scalar function.
Okay.
So it's simpler. For a massive particle, right, just adding a mass, right? We got this into P mu minus m squared is equal to 0. So the quantum mechanical would be minus D'Alembertian minus m squared phi is equal to 0. And just, reversing the sign, we get D'Alembertian plus m squared phi is equal to 0. Which is pretty much straightforward. It's known as the Klein-Gordon equation.
In textbooks sometimes it go with a line on it, right? The inversion, I think it's something
I'm not familiar. And as the name implies, this equation, of course, was invented by Schrödinger. Found by Schrödinger. Before he wrote the equation that wrote his name. And he did not like it. That's why he kept on working on this equation. Why? Look looks quite good. What's the problem with that equation? Yeah.
Negative mass is also
Mass, we put a mass term, not negative.
yeah, but for particles with negative mass, it will be
You have a negative, not mass. You have a negative energy.
Energy solution.
You have a negative energy. Is that a problem? First, it is a problem. We don't understand what it means. Let's say we can think of a way of overcoming this. It leads to an even much bigger problem. Does that mean if you know? Did you see this Klein-Gordon equation? Negative energy is something which we can still live with somehow. Did you see that? Did anybody show you this equation? No. Okay. So I'm showing.
in
Right?
in mathematics for physicists, we
No, it's okay.
did
So true, it's not taught in quantum mechanics, it is relativistic. So what about the negative energy solution? Negative energy solution, what? It leads to negative energy solution. What does it mean, negative energy solutions? So if we have a solution, let's say psi is E phi. Phi is equal E plus minus I P mu x1. Right, so we plug that in the equation, put in Klein-Gordon equation. What do we get? Deriving it twice, so I have a minus p mu plus m squared is equal to 0. E to the I can cancel. Is equal to 0. Which means that the energy E is equal to momentum p squared plus m squared, but square root of that plus minus. So with the plus we're happy, with the minus we have a problem.
what is the problem?
What? What does it mean, negative energy? Okay. You could say, like in classical physics, often we encounter, not often, but sometimes we encounter this type of problems, and then we say, okay, this is not physical solution, so we just ignore it. Right? In quantum mechanics, it's different, right? Because all the solutions form a space, right? It's a Hilbert space. So what is the meaning of negative energy solutions in a Hilbert space? Right? We have a complete set of solutions. But as I said, this is the least of a problem. There are ways of overcoming this problem, actually. I'll show you that in a second. There is a much bigger problem. And that is, what is the meaning, what is the physical interpretation of a solution with negative energies? Right, so in quantum mechanics,
Classically, you can just say the potential plus plus half.
No.
Okay.
No. What's the meaning of wave function? In quantum mechanics, QM, a wave function, psi. Right, let's say we have some wave function psi of x. Means, what does it mean?
The square is probability.
Right. So that tells us something about what is the probability of us to find this particle somewhere, right? So psi means, right? Psi squared psi d cube x is physically, right? Physically, the probability of finding the particle in volume element dqx. Right? That's how we think of psi. That's the way you should think of psi. If you did not do so already. Right? So this is equivalent of identifying the probability density. Did you see probability densities in quantum mechanics? Anybody did not see? Raise your hand. Okay, good. So it means the probability density. Simply because I remember that when I was a student I was confused. Probability density. So probability density, which is noted by rho, of x and t, is psi star of x and t times psi of x and t. So, if the particle we have does not decay, so no decay, what does it mean? What? Yeah, so it stays, right? So probability, the particle cannot disappear, cannot just get lost anywhere, right? It's there, it stays there, somewhere in space, right? So there is a probability is conserved. Probability is conserved, right? The particle can move from one place to the other, but overall, it's not. It is somewhere. Right? So probability is conserved. So we can look at the probability current density. So define the probability current density denoted by J. It's a vector. X and T. Is the flux of probability across a surface element. Is the flux of probability across a surface element.
Gradient of rho.
Yes. J ds. From here on, we can simply think of probability as just a point-like particle that is somewhere in space and can move from one place to the other, or a fluid flow in a river. Doesn't matter. It's the same. It's the same thing. So, what is the rate of change of finding the particle in volume element B? So dt integral rho dV. So again, so now I'm just thinking of it as now having some flow. This is I have some particles in here. There's a flow of incoming particles, flow of outgoing particles. So integral dt of rho dV, right? This is the dV here. The volume element is a what? It's just the flow of particles going out and going in, right? So it's just minus integral over the surface S A dot ds, which, using the divergence theorem, is just minus integral over the volume of blah blah dot j dot of j dv. And we did not specify the volume, it's true for any volume. So we ended up with an equation which is essentially a continuity equation for the probability, which is blah blah dot j plus dt rho is equal to 0. That's a very famous equation. It's a continuity equation. You find it in fluid dynamics. You find it anywhere there's a flow of something. You find it here as well. Just don't think there's something special about that. It's only the only thing that is unique here is the look at the rho as the probability density of a function. Now, let's go back to the Klein-Gordon equation. Right, so if we go now to the Klein-Gordon equation, what is the continuity equation associated with the Klein-Gordon equation? So the Klein-Gordon equation minus d mu plus m squared phi is equal to 0. I'm going to multiply that by minus I phi star.
Wait. Why are the derivatives with a negative sign?
That's the way Klein-Gordon equation was built. Did I miss anything here?
It's with a positive sign. If the mass is with a positive sign, then so are the derivatives. Unless I missed something.
Shake it out. It's not going to make any difference because I'm going to take the complex conjugate and multiply, but I will check it out. Okay. Or you'll check it out, actually. So it's written in my notes, I need to check it out one. So add the complex conjugate. So we have an I phi you're right, it's a typo. I think it should be here. I think it is.
It's not because of the I multiplication in the momentum. You need to multiply it by
No, then there might be. You know what? I'm just leaving it now because that's in my notes, and then maybe there is a typo. You'll check it out. And then I have an I phi. It's the complex conjugate, so I still have this minus d mu plus m squared.
In
Phi
one
star.
dimension, it's minus I.
I'm not going to solve it right now.
Yeah.
There might be a typo here. I'll check it out later on. You'll check it out later on in your free
In
time.
Wikipedia, it's with a plus sign, but maybe the conversion.
It doesn't
is
matter
not the
because I'm going to add them. So if there is anything, they will add up to 0. So if there is a typo, then it will cancel anyway. So I'm adding the two terms with the mass will cancel, right? And if there is a minus sign, it will cancel as well because I'm adding them and it's equal to 0. So I end up with an I phi star d mu phi minus I phi d mu phi star is equal to 0. And if I got missed by the sign here, then there will be a global minus sign, which will be in the 0. Again, that's my privilege to make these mistakes, not yours. Okay, so now we can write this down, simply expand the d mu, right? So, yeah, expand and do a little bit of simple mathematical manipulation to write this down as dt I phi star dt phi minus phi dt phi star yeah, because I have the dt phi star which will cancel out, so that's okay. The I of course multiplies all of them, plus blah blah of minus I phi star blah blah phi minus phi blah blah phi star is equal to 0. That's fine.
It's because it's 0, so you can say it's what?
I
That's
just
zero?
open up the d mu dt dt.
Okay.
Nothing fancy.
What about the mass?
Cancels. I added up.
Cancel.
I added up in the cancels.
Okay.
Right? Because there's an extra minus sign here, and a minus sign, and I when it's a complex quantity. So the mass term cancels out. So having this is a Klein-Gordon equation, plus it's multiplied by minus I phi star plus a complex conjugate. Add that together, I get this equation. So now we can identify J mu, of course rho and J mu, J, sorry, vector. This is just I phi star d mu phi minus phi d mu phi star. And this equation is really equal to the conservation equation, to the continuity equation. So the conserved current density, which is this one, right? When I identify J mu, this term is just this equation, sorry, is just this equation. So I can write this equation as d mu J mu is equal to 0. Yep. Everybody's happy?
Okay.
Yeah, I keep the I here because to make sure these are real. If I put the I to be real, I don't have to put the I because anyway it's just a constant. So with this identification, we can look again at the plane wave solution. So if now we have phi, so plane wave solution, plane wave solution means that phi is equal to n e minus I mu x mu.
That you get from this equation the m minus sign between the gradient of J and
Did I get what?
a minus sign between them.
No.
That's good.
That's fine. Phi is n e minus I e mu x mu. So if I use that in the definition of J, which is written here, phi star d mu phi, that means that J mu, say rho, just like the zeros component, so it will be, we got rho is equal to squared E J is equal to squared P momentum, or which we can write as J mu is equal to.
So the problem is that the probability density will be negative.
Exactly. So J mu is 2 squared times P mu. So now you immediately see the problem. So if E, therefore,
So for a solution for which P0 is E smaller than 0, we get that J0, which is rho, is also smaller than 0.
But this is not the row that you defined earlier. The row, the original row was
This is row.
5 times 5.
No.
And the
This
step comes
is
from
the row for the Klein-Gordon equation. Think of it a little bit. This is the row for the Klein-Gordon equation. The equation that will, the wave function that will fill in the Klein-Gordon equation, this will be the definition of rho for this wave.
It is a continuity equation, but it's
This will be it. Think of it a little bit. Yes.
Why there is not absolute value on E?
E is just P0.
On,
Just a P0. So.
okay.
So that's a real problem here. That we not only have negative energy solutions, but the interpretation is that the probability of finding a particle having this negative energy solution is negative, which does not make any sense. So, negative probability energy density.
אולי ביקום מקביל.
That's the reason why it was thought this equation is not physical for several years. Then what happened? It was in 1934.
Antimatter.
Anti-particle.
I mean, I read the.
You read my lecture.
Yeah, so.
That is the problem. You should not read my lectures. You read the textbooks. The lecture not is for me. You should read the textbooks and the material. Right. You get negative energy solutions. Right. Right. So 1934, it's Pauline Weisskopf, that's the positron. Right. Now, positron, now we can have a different interpretation, right? So one thing is we can say, okay, maybe we can simply add a charge to that equation. Then you have a negative and positive charge. That does make sense, right? So it's not a physical example. I'll show you on Thursday why it isn't, right? But we can think of adding charge. Right. Then we can think of the electron current. In J mu, the electron, V minus E times 2n squared in mu. Now I'm saying right away, this is not physical solution of the electron. Physical solution for the electron is Dirac's equation, because the electron has a spin 1/2. So it's not described as spin half particle. But now the interpretation is that this probability current density is just the charge current density. That can be negative. So Richard Feynman took this interpretation one step forward. Right, so Feynman and Stackelberg. So Feynman and Stackelberg. Stackelberg. Right. So okay, if we look at the probability current of the positron,
J mu of the positron, it will be a plus E times 2n squared p mu. So you can think of it as this is equal to the probability current of the electron with the negative charge and negative momentum. So this is equal to J mu E minus, which is minus E times 2n squared times minus P mu. What's really written here? It says that emission of a positron with some momentum P and charge E is equal to the absorption of an electron with negative momentum and negative charge. Mathematically, this is correct, of course.
For every
Right. So, and what's the relation between these processes?
charge and particles.
Now, emission of a positron,
I reverse
reverse in
the time.
time. That's a time reversal.
The time direction drop.
This is a time reversal, right? And that's why, remember that when we plotted Feynman diagrams, right? So it's the same interpretation up to time reversal. So, same
So there is time operator or
Up
something
to-
like that.
time. No, time operator is something else at the moment. But what this interpretation shows, according to Feynman, right, is that we can think of a positron going in some direction as an electron going in the opposite direction and backward in time. Mathematically, it's identical. Positron going forward in time is equal to electron going backward in time. Cool.
Yeah.
That's why, right, when we plotted Feynman diagram, right, for an electron, we put the arrow in one direction, right? So that could represent an E minus with an E energy greater than 0. And the positron would be in the opposite direction. These more than 0 and these are equal. That's where it comes from. It's an interpretation, basically, which is mathematically fully correct. Yeah? So a positron propagating forward in time is identical to electron propagating backward in time. Quite cool. Yeah, fine. Which is, of course, if you can think of it, that's a simple way of understanding that is to write down, the wave function will be E minus I et, which is equal to E minus I minus E minus t. Right? Negative energy particle propagating backward in time is the same as positive energy particle propagating forward in time. Yes, okay, this is one example. Now there is, that's an example of what's called CPT. I did not say I speak about C, I spoke about P. And there are combined CP and CT, and now this is CPT. It's a different symmetry which I'll describe. We will discuss in a few lectures. I just hope I have enough lectures for it. All right. Right. Now I would say something. Okay, so this is one way out, my solution out with some physical interpretation. A deeper issue is that the Klein-Gordon is not really able of representing a real particle. Why? It goes back to the fact that particles can destroy and disappear. In quantum field theory, that happens all the time. Klein-Gordon at the end does an equation describing only a single particle. So they cannot fully describe the physical.
לא יכול להכתיב את זה, זה משהו.
Okay. Questions? Once you start thinking of time as just a coordinate, it gets easier to imagine all the things, right? You don't have a problem for me going plus x direction and then in a minus x direction. You're used to that. But you do have a problem of things going backward in time. All right. Questions? Okay. As I mentioned, Klein-Gordon equation is not a physical equation. It was replaced by the Dirac equation describing the electrons. But there is a slight modification to it, which is called the Procca equation, which is physical. Klein-Gordon equation, it's a very good example of demonstrating various things. But it deals with a scalar particle. What if you have a vectorial particle? So, wave equation
Right, so how we deal with the negative probability? Just accept it to be a reversal in time.
So that's interpretation. As I said, Klein-Gordon equation is not physical at the end. Right? That's the reason why. It's because we have this negative probability. But one way out is to say, okay, we can write a similar equation not for the particles, but for the charges of the particles. Okay? It will still not represent the electron because it does not have the spin of the electron, but it gives you a nice idea of ways of getting out. A different way of thinking of physical scenario. Okay?
Yes.
So, let's talk now about a wave equation and degrees of freedom for a vectorial massive particle. So we simply change the scalar in Klein-Gordon equation with a vector. So Lagrangian plus m squared of a vector, which we'll call it w mu, is equal to 0. This is a vector. This equation has a different name. It's called the Procca equation.
Just switch phi to vector, not spatial. There is neither a new name for this equation.
Of course. Procca wrote an equation, so it must be on his name.
But it's
No,
pretty
it
much
has,
the
it has a
same.
different physical interpretation, right? Because we have a vector here,
Yeah.
right? That does have a spin 1, right? Like the photon has a spin 1, right? This vector will have a spin 1. Which vectorial particles you know that have spin 1? This we actually do know.
Photon?
What?
Photon?
Photon is not massive.
Mesons. No, it's there.
No, I don't think so. No. Will be, no. What you have will be the vector bosons, the W and Z. So this represents the W plus minus and Z0 boson. Represent W plus minus and Z0 bosons. So the mediators of the electroweak interaction. So this will also have a J PC, which is 1 minus minus, for the same reason as the photon, similar to photons. Okay, how did we get the proper equation? So let's talk about gauge freedom. I want to remind you, right? We got the photon, right, by writing down the Lambertian of A mu is equal to 0. Right. We basically repeated the same step, but now we added a mass. Yep.
So we will change it.
But we did something else to get the photon equation. What did we do? It's actually written.
Again, what?
I said the Procca equation is derived in a similar way for the equation we had for photons, right? Just with a mass. It's not just a just, right? We said for the photon, we wrote down this equation, the Lambertian of A mu equal to 0, and we solved it, right? And we got this factorial result, which had two degrees of freedom, which we call polarization. Now we want to do the same. We want to repeat the same steps for the W and Z. For the vector bosons, the difference is that now they do have masses. Right? So we're going along the same line of reasoning as we did for the photon, and then we got stuck on something. What did we get stuck on? Here, which we did not get stuck here.
The Lorentz transformation.
The what?
The Lorentz constraint.
Gauge. Yes. We use the Lorentz gauge. Right? We had the freedom to choose a gauge. Right? So we wrote the equation. Now we no longer have this freedom because we have now a new constraint. So, we first applied for photons. We had that. Then we first applied the Lorentz condition. Lorentz condition, right? B mu A mu is equal to 0. Well, the non-homogeneous equation, the Lambertian of A nu minus D nu B mu A mu equal to J nu. Now we could do that because we chose the Lorentz gauge. I'm just reminding you of the way we derive the photon equation. What do we do now? When we put a mass term, we no longer have the gauge freedom. So it goes away. But when adding mass, the gauge freedom disappears. But the Lorentz condition still holds. But Lorentz condition still holds.
You can always do a trick and add the term that will cancel the mass.
No, but I feel don't need to.
I
cannot do that many tricks.
And
no, let's just do it. What does it mean a gauge freedom, right? That we can take the A mu, gauge freedom means that we can take A mu, turn it into A prime mu, which is A mu plus d mu lambda for some lambda. Just stay with me. If you have questions, there will be time for questions. That means we can do that and the equation remains the same without changing the equation. Now what happens if we look at the equation, D'Alembert-Yan of A mu plus d nu, A nu plus d nu lambda minus d mu, equation we have here. A mu plus d mu lambda equals j nu. So we're using this equation. And this is identical, or no, I should say these are identical. These equations, these two equations, right, are identical, provided that D'Alembert-Yan d nu lambda minus d nu D'Alembert-Yan of lambda is equal to 0. Or I should say, but these are differentiation, right? You have d mu, and d nu, and you can always change the order of differentiation, right? So it doesn't matter. So this is always true. But order of differentiation doesn't matter. Can be changed. So true. So, if we have no sources, there is no J nu, right? So, for no sources, the equation for the photon is that without the sources. D'Alembert-Yan of A nu minus d mu A mu is equal to 0. So replace now D'Alembert-Yan with D'Alembert-Yan plus m squared. Then we'll get D'Alembert-Yan plus m squared of A nu minus d nu A mu is equal to 0. Which is not gauge invariant. Alright, with different gauge, we'll have an extra term. Should come here, m squared plus d nu lambda times m squared. Get an extra term, m squared d nu lambda. So we basically say that the mass term breaks the gauge symmetry. Is that clear to everybody? Yeah. So we say that the mass term breaks So this is not a gauge invariant. But somehow it does fulfill the Lorentz condition. But this equation, right? But it does fulfill that Lorentz condition. What do? We just take this equation and derive with respect to nu. So from this equation, we add up the nu. We get nabla plus m squared d nu a nu minus d nu d nu d nu d mu a nu is equal to 0, or nabla plus m squared d nu a nu minus the Lambertian of d mu a mu is equal to 0. This and this cancel, so we have that m squared d nu a nu is equal to 0. Which is quite cool. So, even when adding a mass term, we still have this gauge symmetry at the end.
אסף, המשוואה שם זה שיקול רוקה?
זה פה. This will be for photon. This is massless, which is a photon. This is massive, which is proper.
Massive, but without zero.
Yeah, no currents. Essentially what we have here. Okay, so now we can look for solutions to the proper equation.
Like if you said it's described W and Z, and
Yeah.
they have a charge, so no, it doesn't.
Okay. Now, let's see. So I'm looking for solutions. So again, for free particle, so no sources, look for a solution of the form A nu is A epsilon nu E minus I P mu x mu. Of course, now we have P mu is just B squared is M squared. So again, this is the plane wave. How many degrees of freedom will we have? 4. Yeah, it looks like a 4 for the epsilon nu. A is just a constant, right? Normalization. This is the vector representing the degrees of freedom. Right? Different polarizations if you want. This is just a plane wave.
You have 3 degrees of freedom left.
Right. Why?
We have one
Because
equation.
one goes for
One, exactly. So we have the Lorentz condition. The Lorentz condition can write as P nu epsilon nu is equal to 0 removes 1 degree of freedom. Removes 1 degree of freedom. So it means that we have 3 degrees of freedom. Independent. So that means that the Z0 and the W plus minus have 3 independent polarization states. So again, without loss of generality, we can take the Z or the W to be traveling in the plus Z direction. So for travel in the plus Z direction, 2 degrees of freedom you'll know immediately, which will be what? Two degrees of freedom, should say right away what it is.
X and
Right.
Y.
What are the degrees of freedom here?
Density.
This will be the polarization states of these particles, right? You can have it along the X and along the Y, but a better choice would be circular and the same as we have. Essentially, what I was looking for is somebody said the same as the photon. Right? We have 2 degrees, which is transverse to the direction of motion, so the same as the photon. Right? So 2 circular polarization states. 2 circular polarization states. Epsilon mu minus is 1 over square root of 2. I write down all 4 with 1, 0, 1 minus I 0, and epsilon mu plus is minus 1 over square root of 2, 0, 1, I 0. So 2 of the 3 we already know. What is the third one?
It should have a time component.
What?
It should have a time component.
Correct. Why? It's true.
1, 0, 0, 0.
No, that's true. It should have a time component. Why? What do we know about the third polarization state?
It's perpendicular to Z.
It's perpendicular to Z. It has to fulfill this condition, the Lorentz condition. It has to be perpendicular to both of these 2 polarization states.
Yeah,
Right? To be independent. Right? Have to be independent. To be perpendicular.
and
It has to fulfill that.
this is 2x and y, so it must.
So we call it a longitudinal polarization state. The third is a longitudinal polarization state, which is orthogonal to the other 2. Orthogonal to epsilon mu plus minus, and fulfills the mu epsilon mu equal to 0. So we'll have it epsilon mu longitudinal. Normalization here will be 1 over m, and we'll get indeed pz 0, 0, and e. Why did I put the 1 over m here?
Normalize.
Normalized to what?
Epsilon. Yeah, the normal fit is.
What's the difference? One of the differences, key differences between a massive particle and a massless particle?
travel to P if you have a...
Massless particle will always travel in the speed of light. Massive particle, I can always go to a frame in which it is at rest. In that frame, how would this polarization look like? When it's at rest?
0, 0,
0, 0, 0, 1. That's why the 1 of rank, right? In the rest frame of the particle, we have epsilon L mu is 0, 0, 0. Quite cool, isn't it? All right. More questions about that?
You can go to in the rest frame, and there's not supposed to be something with on the time component. No.
No light. 0. I mean, in that rest frame, right? Just sitting down there.
Proper times. Proper
I don't need. No, this again. This is a polarization vector. Of the
Oh,
particle.
okay. Okay.
It's not normalized if you're not in the rest.
It's in the rest. It's in the rest frame. It's normalized.
But not in the rest.
On the rest frame, we get some component piece of that.
No.
It's not normalized.
Why?
It isn't normalized.
It's normalized.
Oh, you have more than one in the data?
Sorry.
You assume that you have
I assume that it moves only in the z
Ah,
direction.
okay.
Travel in the plus z direction. Questions? Okay, good. If there are no questions, then let's move on. So we'll start discussing now Dirac. Dirac equation is very central to particle physics. It's a quantum field theory course. We spend, I don't know, 1/3 of the course on explaining what's going on there. We're not going to do all that, but we will give you the basics.
And the other two surfaces. There is
Understanding the language. But I'll do some derivations here before the Dirac. Right. So Dirac equation. As I said, the motivation is that the Klein-Gordon equation, which is a serious attempt of getting relativistic equivalent of Schrödinger's equation, failed. It does not work. Okay, I mentioned the Feynman-Stuckelberg interpretation with negative energy solutions describing antiparticles. And the other problem with the Klein-Gordon equation is that it does not represent decay of particles or creation of new particles. So we really need a new interpretation. So Klein-Gordon equation, motivation. We should put it not here. Motivation. Klein-Gordon equation. And the negative probability. Though the Feynman-Stuckelberg interpretation. Interpretation of antiparticles. And we have does not describe decay or creation. there's an interesting historical story, right? Dirac was searching to a new formalism of how to derive this relativistic quantum mechanics. And he came out with an equation which did not solve these problems, but did manage to provide the right description of spin half particles. And it's built into his formalism. I put some mark here that we need to speak about representations and Lorentz group. We're not going to do that all the time. Dirac provided found natural explanation to spin half particles, aka fermions. Basically all of them. So let's start to derive it. So the starting point of the Klein-Gordon was the relation E squared equal P squared plus M squared. Yes. Right. And that led Klein-Gordon to suggest an equation which is second order in derivative. Klein-Gordon suggested second order equation. And Dirac looked for a wave equation which is only first order, both in time and in space. By the way, did any of you encounter Dirac equation anywhere? Yeah, I would be very surprised if you did, because this is a quantum field theory. Somebody might mention it to you. So. Okay, so Dirac looked for a first order equation, both first order in time and space. So that means first order wave equation. So the solution will have the general form. It looks something like E psi. It will be an operator. Is alpha dot P plus beta M psi. So promoting E and P into the operators will give us I dt psi is minus I alpha j dj plus beta M psi. So far so good. What is J?
Index 1 to 3.
1, 2, 3, right?
Yes.
There's no time derivative here. This is the spatial derivative. P is momentum. Yeah. Alpha J.
Particles, right?
Yes. Alpha J and beta. What are they? They are constants. And importantly, they are not necessarily going to commute with each other. In fact, as we're going to see, they are not. So they cannot be represented by simple numbers. Okay. Alpha J, alpha, vector, and beta are constants which do not necessarily, don't need to necessarily commute with each other.
We can assume the change is very small, right?
No.
No?
At the moment, these are constants. I don't say anything about these constants.
Okay.
I just say that I'm not limiting myself to simple numbers that will inevitably commute. I tell you these are constants. Now, if this equation is to represent a physical particle, it does have to fulfill this equation as well. Right? So we do need to get essentially the Klein-Gordon equation. So this equation must satisfy Klein-Gordon equation as well because of that. Right. This has not changed. So what do we do? How do we get from this equation to that equation?
Apply
To
again.
square it, basically, right? Apply it again, right? We square it. So we have to square this equation by simply taking the time derivative, and remember that I just wrote down that the alpha and beta do not necessarily commute, so I have to be careful. So if I'm taking the time derivative, then I'll get a minus d squared t psi will be equal to minus I alpha j dj plus beta m, and then the time derivative will be minus I alpha k dk plus beta m psi. Nothing alarming. Since it's going to be tricky, I'm going to expand that. And so expand that equation. Expand. It's not really tricky. It's an algebra which can be confusing. So expand. Expand. We get d squared t of psi is equal. Now I'm just going to open one by one all the terms here. So I'm going to get alpha x squared d squared x psi plus alpha y squared d squared y psi plus alpha z squared d squared z psi minus beta squared m squared psi then we have plus alpha x alpha y plus alpha y alpha x. I write it explicitly like that because I do not assume that they commute. D squared psi over dx dy plus alpha y alpha z plus alpha z alpha y d squared psi dy dz plus alpha x alpha z plus alpha z alpha x d squared psi dx dz plus I alpha x beta plus beta alpha x m dx psi, and the same for y and z, plus I alpha y beta plus beta alpha y m d y psi plus I alpha z beta plus beta alpha z m dz psi. Okay? I just expanded that. That's all. Yeah, exactly. But there's nothing conceptual here.
I think you have it. Oh, never mind. It's not a typo. It's just an X which looks like a Y.
It's preparing for a pool. Such is life. Now, this has to reduce to Klein-Gordon equation. This needs to reduce to Klein-Gordon equation, which is what? D squared t psi is equal d squared x psi plus d squared y psi plus d squared z psi minus m squared psi. So this gives us
A lot of zeros.
this gives us constraints on the values of alphas and beta. Right?
Yeah, a lot of zeros for the
So this can happen. This is true if alpha j and beta satisfy so alpha x squared is equal alpha y squared is equal alpha z squared is equal beta squared is equal I. I is the identity matrix. Then alpha j alpha k plus alpha k alpha j is equal to 0 for every j which is not k. And alpha j beta plus beta alpha j is equal to 0. I is the unity.
They are anti-commute, right?
Yes. Thought you're gonna love that, right?
Yeah.
Good.
Looks like
So-
very good, something like that.
This is an anti-commutation relation, right? Remind you, commutation relation. If I had a minus sign, it would be a commutation relation, right? It's called Grossman algebra, if you've ever seen it, right? This is the anti-commutation relation. And the fact that the alphas and beta must satisfy these anti-commutation relations means that they cannot be simple numbers. Right? The simple numbers do not obey them. They have to be matrices. So that means that alpha j and beta are not numbers,
How many equations that provide us?
but matrices. Well, we're going to have 4 of these matrices, because j goes from 1 to 3, and 1 for beta. And now these matrices obey several conditions, several properties, and I think we're running out of time, so we can go over the properties of these matrices on Thursday. But
We have more equations than matrices.
מטריצה, יש לו מלא פרמטרים.
these are matrices.
Yeah,
And there will be
so-
several conditions for these matrices.
So
There
we
will be
have
traceless
more
matrices, the eigenvalues of plus minus 1 that have certain dimension.
מלא פרמטרים.
Okay, now, but again, alpha and beta, alpha j and beta, these are constants. They multiply the Dirac equation. I just wrote it down and I erased it, right? These are just constants.
Alpha is a vector, so you have 4 components. No, 3.
It's a 3 vector,
Yeah.
but it's not a
Yeah.
vector in the sense. It has alpha j's are constants that multiply the momentum.
Okay, and beta.
Beta is a constant
Not
that
a
multiplies
constant.
the mass.
So
Now, this constant does not have to be a number. So in that sense, alpha j's are not necessarily representing a vector in the sense that you're thinking of.
operator.
Not even that. Let's
Okay.
discuss that on Thursday. Right? We will. You'll see. Okay. Now they're not numbers. They can be represented in many ways, but the simplest way is matrices, and these matrices have to fulfill certain conditions, which I'm going to derive. It will take me 10 minutes, but we're already out of time. to derive the certain conditions set by these matrices.
מהרצון של חברת אייזנברג?
לדעתי לא, אולי לדעתי לא. All right. Questions? We'll continue to discuss that on Thursday. Now, guys, I do want to ask you. When we reach the stage, if initially I could imagine that some of you may know some things, or that these are things that I'm pretty sure that you have not seen in the past, and I'm aiming. This is aimed toward third year. I know some of you may not be third years here. It's aimed toward knowledge of third year, but that does require you to a bit of thinking. We're going to deal on Thursday with Pauli matrices a little bit. If there are things that are not clear to you, go and read them, and come and ask questions. Make sure that this is. I may not know the answer right away, but I will bring the answers as soon as possible. All right. So do your homework. Not just the homework you're given, but make sure that you are constantly with it. All right. All right, guys, at home. Okay, so Thursday we have a lecture. It's going to be longer than the usual, 3 hours lecture. See you on Thursday then.